Good evening, folks. Um, okay, so we're going to see how this works out with recording stuff for statistics. Hopefully, this works better um, than it would be if it was going live, only so you'll be able to go back and take a look at it to help with homeworks or for references or those sorts of things. So, I'm going to see what we can do here. So, given the conversation that we had before the break, as we talked about in class, my assumption was that um, in Conduct 1, y'all actually went over the assumptions of regression. So, given the fact that there was some level of confusion when I started using terms such as multicollinearity and everything else, there was looking confusion on some folks' faces. I wanted to make sure that I went over the assumptions. It's good to know these assumptions because some of these assumptions hold regardless of the type of regression that you're talking about. So, and we'll get into some of those things, but for linear regression, these are the assumptions. So, the first assumption that you should have, so the first two assumptions, you really don't have to test for those. The first assumption is that your dependent variable is at least interval level data, so interval or ratio level data. So you should have a continuous outcome. So, um, so if you have a limited or categorical outcome, such as nominal ordinal level data, you cannot do linear regression. Actually, the purpose of this class that we're now Conduct 2 is how do you analyze outcomes that are measured in a more categorical fashion or a limited fashion, limited fashion. So, um, so that's the whole purpose of the class. But thinking about linear regression for a minute, so you want to have at least interval level data, so interval or ratio. The second one is that the predictors in your model must be continuous, so interval or a ratio level measure, or they have to be dummy coded categorical predictors, because that eases with interpretation. So those are the first two assumptions. So, but you can't test for those. That's just a matter of how your predictions and your outcomes are actually measured in your model. So hopefully that went over well. So the data that we're going to be looking at to test the remaining assumptions of regression, I am going to post this data for you, or at least the link, send y'all the link for it, and y'all be able to download it and incorporate it into um, this data file that we're going to be using. So, that being said, the first thing that we're going to do once you get your data, so I already put it in here, as you can see, but if I'm putting it in here again, you put in the use command, then the website for the data, and if you then hit return, you'll see the data comes up. As a little bit of background, the data comes from California. I believe the state's Department of Education collected data from 400 elementary schools in the state of California. And some of the things that they looked at was each school's academic performance index across 2 years from 1999 to 2000. And if you look over here where the cursor is, you see API, which the academic performance index for 1999 and the academic performance index for 2000. So that's actually going to be our outcome. So if you actually run the model, a linear regression, you're regressing the academic performance index for 2000. And these are scores, I believe they range, I want to say probably somewhere between 200 and 700, 200 and 800, somewhere around there. The predictors in the model are meals, and this is the percent of students in the school who get free meals. And some college, this is the percent of parents who has some college education. So these are the models. So this is a multiple linear regression. So you have more than one predictor in the model. If it was one predictor, it will be called a simple simple linear regression. So we have more than one predictor in the model. So if you do that, so regress your outcome, and then you have your predictors following that, this is what you get. So as you can see, it tells you the number of observations in the model, which is 400. Um, you have your F value and the significance of it. The F value tells you it tests the null hypothesis that all of the predictors in the model are equal to zero. Remember, is that zero, meaning there's no relationship. So it tests that hypothesis that all the predictors are equal to zero. You see that the probability is less than 0.05, which means you're rejecting the hypothesis. And you can say at least one of the predictors is significantly different than zero or not equal to zero. So you have your R square. And you see that the model was pretty good because just these two predictors in the model, when looking at academic performance index, you'll see that it's explaining over 80% of the variation in the outcome of academic performance index. See, I guess I'm not feeling well. All right, so in any event, that's the model, but my assumption is that you, and hopefully it's not a bad assumption, that you did go over um, linear regression and conduct one. So I'm not going to focus on this too much. So when you're looking at the model here, so if you look at meals, so the coefficient is it's a negative coefficient. You see the t-value, and you see that is less than 0.05. So what that telling you is for every unit increase in the percent of students on free meals, the academic performance index for the year 2000 decreases by 3.949 points. So that's what that tells you. In other words, as percent of students on free meals go up, then the academic performance index for the year 2000 goes down. Some college is significant, so it's a positive coefficient. You'll see the significance level is less than 0.05. You see the t-value is 3.06. So what that tells you, for every unit increase in the percent of parents who have some college, the score on the academic performance index for the year 2000 also increases by 0.8476549. So that's what you have here. So here's your model. So now we have to figure out, are the assumptions of regression met? So the first assumption of regression. And you can do these in any order. So the first assumption is that there is a linear relationship between your predictors and your outcome. So again, a linear relationship between your predictors and your outcome. So if you're looking at um, to see if the linearity assumption is met, you can do a scatter plot. So you can do this multiple ways. So there are different ways to test for the linearity assumption. This is just one way, but there are multiple ways in case other you know some other ways to do it. So you can do a scatter plot to see what the relationship actually looks like. So the command is two-way scatter for a scatter plot. You put your outcome, which is the Academic Performance Index 2000. And here I'm doing it one predictor at a time. So I'm doing meals. I'm looking at the whether or not there's a linear relationship between each predictor in the model, which is meals and some college, um, and academic performance index. So technically, that's all you need. However, I put this other part after the command because this will actually draw a line of best fit, which is the L fit. So you can actually see where the best regression line actually fits here. So two-way scatter API 00 meals, which is the first predictor in the model. Then to draw the line of best fit, open parentheses, L fit, then the same thing, API 00 meals. So that's your command. Once you do that, click on return. And what you will see here, and that extra command, the lfit, that's what draws this red line that you see right there. So what this tells you is, and as you can see, there's a negative relationship here. So that's telling you as percent of students on free meals increases, the values on Y or your outcome, or academic performance index, is going down, which is why the line of best fit is going down this way. So this actually, you can even look at it and see that um, that there is a linear relationship here between them. So as percent free meals go up, then API in 2000 actually goes down. So the assumption is met when looking at meals. So if we do the same thing but swap out meals for, actually, let me just go to here. So again, we have the same syntax, but we just swapped out meals for some college. You see there is a linear relationship here also. So you see that according to all of these, according to this scatter plot, this is saying, okay, as the percent of parents with some college, as that increases, then their scores on API in 2000 is also increasing, which is why the line of best fit is going up this way. So this is a nice test to see whether or not the linearity assumption is actually met. I hope that makes sense. If it does not, then definitely feel free to ask me some questions. Clearly, we're not live, so we can't do it then. But whenever I set up chat, or somebody can, or y'all can shoot me an email or those types of things, we can get together on Skype and everything else. So that is the first assumption of regression. So the linearity assumption is important because remember how you interpret your coefficients for regression. For every unit increase in x, your predictor, y goes up or down by this amount. So there's not a linear relationship. Then you won't be able to make the interpretation of as one goes up, the other one goes up or down by this amount. So that is why that is important. So the second assumption of regression is no multi-collinearity or no perfect collinearity. So this just means that there's no highly correlated predictors in your model. So let's talk about why this is important. So think about it in terms of if you're talking about school age kids. So let's say you're talking about you're looking at predictors in the model, and you look and two predictors you have in the model are age and grade. Well, especially when you're talking about school age kids, age and grade, you're in essence measuring the same thing. Because if you're talking about, for instance, kids in high school, let's say, well, typically your ninth graders are 13 and 14. Your 10th graders are 14 and 15. Your 11th graders are 16, 17, and your 12th graders are 17, 18. So typically, age and grade pretty much are the same thing. So if you then include both of those predictors in the model, age and grade, the problem with that is going to be that how do you know how much in your outcome is being explained by each one if both of them are pretty much measuring the same thing? So it allows you to know how much of each predictor is explaining what in terms of your outcome. So you got that shared type of responsibility. So if they're too collinear, if they're too correlated with one another. So collinear only means correlated. So you can't have factors in your model that are too correlated or too collinear with one another. So let's look at this. So there's a couple ways to doing this. All right, let's actually get rid of this. All right. So if you do the um, CORR, that's correlation. I put API 00 just so you can put the outcome in there, even though it's not needed. But I put that in there just so people can have an idea of how correlated the predictors are to the outcome also. So when you have your syntax here, you're saying so correlation, everything you have in the model, your outcome, and your two predictors. Then you hit return. So what this tells you, ignore the ones because here you're just correlating each predictor with itself or each factor in the model with itself. So API 00 correlated with API 00 is 1 because it's the same thing. Meals 1, some college 1. So that's not a big deal. So correlation goes from -1 to 1. 0 means there's no correlation. So typically, if you see correlations above zero point 0.7, zero point 0.8, whether positive or negative, then that's telling you that that the factors are correlated pretty highly. Because the closer it is to 1, the more strongly correlated the factors are. So what this is telling you here is you have zero point 0.9, but that's okay because here you're talking about the outcome. So it's just saying that meals are highly correlated with the outcome of academic performance index. That's fine. Um, that's fine because the multi-collinearity assumption is based on the predictors in the model, not the outcome. So, so that's okay. So, but if you're looking at the predictors in the model, it's really saying like, okay, what's the correlation between meals and some college? So, meals and some college, it is um, -0.219, and that's really not correlated that highly at all. So you're actually pretty good here. So it seemed like that um, that there's no highly collinear predictors in the model. Seemed like that assumption is pretty met, but there actually are tests for it. So one test is the variance inflation factors. So if you put ESTAT, VIF for variance inflation factors, if you do that and run it, typically if your VIF, your variance inflation factor, is less than 4, if you're some people allowed to go all the way out to 10, but if you're less than 4, then your collinearity is pretty low and you met that assumption of regression. Here is very much less than 4, so it's 1.05. So you're fine here. So I would not. So you met the assumption of multicollinearity. Um, so you met that assumption. If the variance inflation factors, if the VIFs were more than 4, definitely more than 10, then you might consider taking out that collinear predictor because clearly it's overlapping with something, and in essence, you're measuring the same thing across more than one predictor. So you want to take that out of the model. But you actually seem to be doing pretty good here. So, because again, it's much less than 4. So you're fine there. So that is one thing that you can do. There's a collinearity diagnostic package. If you do find it, just put it out there for you. Find it, Colin, for collinearity. If you put that on there and press enter and scroll down, it's right there, Colin. If you want to be able to install this, you definitely don't have to because the VIF is enough for you. But if you wanted to install the collinearity diagnostic package, then you'll, similar to most things in Stata, you only have to install it once and then it's there and you don't have to touch it again. So, but if you did that and then you put in Colin as the command, meals and some college. So again, only the predictors in the model, not the outcome. If you do that and press enter, what you'll get is the VIF was the variance inflation factors. You see it's 1.05, just like it was up here. So you see that didn't change. The tolerance statistics is pretty much the flip side of the VIF. So if you actually take, um, so the tolerance, if you take one, the number one, and divide it by the VIF, so 1 divided by 1.05 gives you 0.9521. So if you have a VIF of at least 0.25, a VIF of at least, I'm sorry, if you have a VIF that's less than 4 and a tolerance statistic that's at least 0.25, then the multicollinearity assumption is met. So you're fine. So I just want to do this so you can see that VIF and your tolerance statistics go hand in hand. They really just the inverse of one another. So I wanted to put that out there to y'all. So that is the second assumption of regression. I hope that makes sense. Click out of here. The third assumption of regression is no significant outliers. Outliers can definitely throw off, can very much throw off your model. That's like if you're, for instance, looking at the average grade for a class, you can have somebody get, folks get 80, 85, 90, 87, 88. Then you can have somebody who gets like a 10. Well, if you're looking at the average, that 10 throws it off because it's an extreme score relative to the other values that are in there. The same goes for regression. When you have a significant outlier, it can throw off the model. It can make the line of best fit. It can make the line of best fit off. It can make something seem less correlated than what it is. So you want to check to see if there are any extreme scores. So there's a way to find extreme scores, but there's actually a packet. If you do find it, extremes, is that first package that you see here, extremes. So you can go on and install that if you want. So as you can see here from even the description of it, it gives you the extreme of the five lowest scores and the five highest scores. So once you install that, you can put the command in there of extremes API 00 meals some college. So you're putting everything in there. So extreme, your outcome, API 00, and your predictors in the model, meals and some college. Then you hit return. It'll tell you what some of the extremes are. Note two values of 903. You see these are relatively close to each other. 369 to 387, really close. 99 to 99 in terms of the values for the meals and some college. But you see, I mean, these aren't really that far off. These are just, again, the most extremes of each one. So for those, for instance, for case number 242, the lowest value, their value on the API was 903. The percent of folks who had free meals at that school was 2%. and percent of parents who had some college was 10%. But these aren't really that extreme. They're really around each other. It's going to give you the five highest and five lowest um, values, even if they aren't extreme. But if there were some extremes here, like instead of saying like 903, if their other one was like, I don't know, 700, that would show here because that would be an extreme. But these are all relatively close to one another. So you see, you actually have no outliers in this data. So that assumption is met. I hope that makes sense. I guess I'll find out depending on the number of questions that y'all have. So the next one is independence of observations or autocorrelation, serial correlation. Different books will call it different things. This just means that your residuals, your error, the error, the error for certain cases are not correlated with the errors of other cases. You'll typically see this most in time series data, which means, for instance, if you're looking at data over time, crime rates in 1999, 2000, 2001, you're looking at the same predictor over time. So crime rates in 2001, the errors, the residuals that are associated with that um, can help you figure out the crime rate, the residuals for that for the very next year of 2000. So they're not independent of one another, they are correlated with one another. Um, so you'll typically see that in time series data. This is cross sectional data. Sometimes you'll see it in here also. How it typically plays out for cross sectional data is when you have nested data. If you have data where you get, where you decided to get sample people from different, neighborhoods within DC. Well, typically people who are in the same community are more similar than people who are from different communities. So knowing about what's going on in one person in a certain community can help you know what's going on with somebody else in that same community. So the residuals of people are pretty similar because people who are from the same community are like than people from different communities, or people who are in the same classrooms are pretty similar than people who are from different classrooms. So if data was collected in a way where they're grouped together by neighborhood or schools, um, or businesses or countries or those types of things, you'll typically see then you have a concern here. There's different ways to address this that goes beyond this class, but that is just one assumption that goes off with it. Homoscedasticity is another assumption. Homoscedasticity pretty much means this is actually better by example. Let's go to one of these scatter plots from earlier. Okay, so here's the line of best fit. So folks looking at this data between percent of students who get free meals with their API, their academic performance index from the year 2000, you'll see this negative relationship, but you'll see, if you were to draw a line through this data, this is the line that best explains, that can best predict the data that we have. So what this tells you with this, like this is the line of best fit. So all these values outside of this is That's your That's the That's the residual. That's your error. At this point, it's the difference between what the value is and what is predicted to be. So this is the line of best fit. This is the predicted value right here, and these values off is the error. These are the residuals. So between here and here, oh, I don't know what I'm doing. Okay, let me stop. Okay, between here and here, for this case, that's the residual for here. For this case, the residual between um, the error between the line of best fit and here, it's this amount for this case, and the same for this case, and the same for this case. For this case, the residual, the error is bigger because it's predicted to be here, but it's actually way out here. So the residual is here. So what homoscedasticity is where if you drew, because you got this error here, if you drew a normal distribution across all of these, um, across all of these residuals, if you drew a distribution around this will say that the variance um, the variance and the residuals are equal, similar. So the variance and the residuals are similar to one another. So not only is the residual the distance between the line of best fit and where the value actually was, but technically, again, if you drew a distribution around here, then there is a variance um, that goes along with each residual point. So if you're trying to do that, it's a RVF plot. This is the residual versus fitted. That's the RVF. Residual versus fitted plot. So residual versus fitted plot. You can only do this after you run the regression. All of these are tied back into the regression model that you ran earlier. So the residual versus fitted plot, comma, recast, and then parentheses, scatter. Are you with me? I hope so. So residual versus fitted plot, comma, recast, open parentheses, scatter, close parentheses. So if homoscedasticity, if the scatter plots are pretty equal and pretty random, above and below the zero. Because remember, if you think about that last plot, there were residuals that were above the regression line or above, sorry, the line of best fit and below the line of best fit. So if the residuals are pretty randomly scattered across the zero above and below, then you meet the assumption of homoscedasticity. Um, if it goes in like a fan type way, so if it goes from wide to narrow or from narrow to wide, it looks like a fan is fanning out, is fanning out either like this or like this. If it does that, you have heteroscedasticity, which then means you do not meet that assumption. So you want homoscedasticity. And honestly, with us, look like we're coming kind of close because as the values increase, it seems that um, the residuals are starting to fan in some. Um, so we might have some issue here. Now, the thing to keep in mind is that it's very difficult to meet every single assumption of regression. Um, but at the end of the day, I still want folks to be able to know what it looks like when you do meet the assumption. But here, you can see, you see that it's pretty wide down on this end. But as the values increase, you see that it's starting to tighten up a bit some. So we might have some heteroscedasticity, at least somewhat. It don't look like it's a lot, but somewhat up in here. So it does be that thing just to keep an eye on. Make sense? I hope it does. Okay, we'll see. Um, the final assumption of regression is normality. Um, so your residuals, some people talk about it as the outcome that has to be that has to have normal distribution. Is not the outcome, it's the residuals, the error. The residuals have to have a normal distribution. So when you look at things like the homoscedasticity and the linearity assumption and everything else, scatter plots are the best thing. But in any event, so if you look at the residuals, so there's a couple different ways to do that. You can actually um, you can actually come up with the values of what the residuals are. So if you put predict, I named it resid. You can name whatever you want. This is what you're going to call your residuals. So this is what you're going to call your residuals. You can name it residuals if you want. You can name it R. You can name it res. You can name it anything you want. You can name it the stars, the moons, the earth. You can name it whatever you want. Just know that you're talking about the residuals or the error at this point. So predict, I call it resid, comma, and then here you actually got to put residuals. So this tells Theta you want it to create the residuals, and then you hit enter, and now you see the residuals have appeared over in this column. You can actually take a look at it if you click browse. You see the residuals are over here now. So these are your residuals. This is your error. This is your error. So there's a couple different ways to see if the residuals, if your errors meet the normality assumption. So the first thing you can do is do a SK test. Let me get rid of this. You do an SK test. So SK test resid, or whatever you called your residuals. SK test resid. So the S is for the skewness, the K is for kurtosis. The skewness, it means if you're talking about a distribution, a normal distribution, The skewness tells you, looks at your tails. How far out are the tails? The kurtosis looks at the peak. Um, what's the peak of your distribution? So you typically want non-significance here. So if your skewness was significant, then that would indicate that you might have some extreme data out there, um, that's pulling the data over to the right or to the left, meaning you got like a pretty big skew, and that would hint that your distribution does not meet that normality assumption. With the kurtosis, same type of thing. Looks at the peak, so you don't want you do not want significance there also. So if you look at um, your uh, your significance level here, you'll see that it's above 0.05. So you're good. So you are okay. Another way to take a look at this is to do a histogram. You can just do the drawing. So the histogram command, resid, or whenever you named your errors, comma, normal. So histogram, resid, or whatever you called your errors, comma, normal. Then hit enter or return. So this allows you a visual of your distribution, and you can see the distribution looks pretty good. So these are your errors. Your errors look like they meet that normality assumption. You see that from the kurtosis, the peak is not too high, and the skewness test, if the skewness was worse, if it was significant, you will see that these tails, at least on one of these sides, come out much, much more. So you see that of the residuals that it meets that normality assumption. So these are the assumptions of regression. Typically, when you talk about other types of regression, um, certain factors still are appropriate, such as no multicollinearity. Um, the linearity assumption um, kind of had to be met because most of your interpretation of things of as one factor goes up, the other factor goes up or down by this amount. Um, so sometimes that may have to be met. We can talk about different tests where the linearity assumption has to be met, at least to some extent. No significant outliers is also one that's very important. The independent of observations, that's important. Again, probably not for conduct two, but in other courses you'll talk about ways that you can deal with data where autocorrelation, where independent of observations, where their assumption is not met. Homoscedasticity. Um, um, Kind of important in other statistics. We'll talk about those as we go on. The normality assumption is not important for other statistical tests that we'll talk about, because here we're talking about the distribution of the errors of the residuals. We're talking about those errors. You're not going to have a normal distribution where you're talking about categorical outcomes such as binary logistic regression or multinomial logistic regression or ordinal regression. Those are outcomes where you're not going to get this continuous um, get these continuous scores, because you typically with those only have a few categories of the outcome. You might have two categories of the outcome or three categories of the outcome, you're not going to have enough to be able to have a distribution that is normally distributed. So um, so that's all I got. Look like this went about 50 minutes. I don't know how this is going to go, so we'll play it by ear and see. So let me know if you have any questions. Thanks, folks.